Case study: Enhancing Cybersecurity with Convolutional Neural Networks, a case study on malware detection and phishing identification. Sophisticated cyber threats demand equally advanced detection methods. In a cybersecurity operations center, data scientist Emily had just finished implementing a novel convolutional neural network model to tackle the increasing wave of cyber threats. Around her, analysts were busy monitoring screens filled with streams of data, but Emily's focus was on her new model, designed to detect malware from binary files visualized as images. Emily's team was well aware of the limitations of traditional signature-based detection systems that relied on known patterns and heuristics. These methods often faltered when facing new, sophisticated malware that could disguise itself or change rapidly. They needed a solution as dynamic and adaptive as the threats they faced. Could CNNs, inspired by the human visual system, be the answer? The CNN Emily deployed consisted of multiple layers: convolutional layers to extract features, pooling layers to reduce dimensionality, and fully connected layers to make final classifications. Each layer played a crucial role, but Emily wondered which specific features her model was capturing. What kind of patterns did it recognize in the binary files? Were these patterns consistent with known malware signatures, or did the model identify new, previously unseen characteristics? Malware detection had entered a new phase with CNNs. Studies like the one by Nataraj et al. Had demonstrated that malware binaries, when visualized as images, revealed distinct textures and structures. As Emily reflected on their findings, she pondered another critical application: network traffic analysis. To test the robustness of the model, her team visualized network traffic data as images, with each image representing a snapshot of network activity over a specific period. The CNN would then scan these images for anomalies, unusual spikes in traffic, or irregular communication patterns. Emily posed a question to her team: how would they benchmark the effectiveness of their CNN model in real time against traditional anomaly detection methods? This led to an intense discussion about metrics, false positives, and the importance of real-time detection capabilities in cybersecurity. Their brainstorming session was interrupted by a sudden alert. The system flagged a potential phishing website. Phishing attacks were notoriously difficult to detect, often bypassing blacklists and heuristic-based approaches. Emily recalled a study by Bonson et al., which had shown that CNNs could accurately classify phishing websites by analyzing visual content. The model focused on subtle visual cues that distinguished legitimate websites from phishing sites. Could their CNN model match or even surpass the accuracy reported in that study? They decided to test it immediately. The model analyzed the visual elements of the flagged website, scrutinizing its layout, fonts, and images. The results were promising. The CNN quickly identified the site as a phishing attempt. But this success raised another question for Emily. What were the most critical visual features that helped distinguish between legitimate and phishing websites? Understanding this could help them improve their model and make it more transparent. The team was now fully engaged, exploring another intriguing aspect of CNNs: their ability to learn from large datasets. They had access to extensive datasets like Google's VirusTotal for malware samples and CITS 2017 for network traffic data. These datasets were crucial for training their models, enabling the CNNs to generalize from a wide range of threat patterns. Emily asked her team, how could they ensure that their models remained effective and unbiased, even as new types of threats emerged? This sparked a lively debate about data diversity, regular updates, and the importance of continuous learning in machine learning models. While confident in their model's performance, the team was also aware of the challenges. One major issue was the interpretability of CNN models. Emily knew that while their model could achieve high accuracy, explaining its decision-making process to stakeholders was a different challenge. Techniques such as saliency maps and class activation maps could offer insights by highlighting the regions of the input data that influence the model's decisions. But how effective were these techniques in practice, and could they be integrated into their existing workflows to enhance transparency? Another concern was the computational cost associated with training and deploying CNNs. Emily's team had access to high-performance GPUs and large memory capacities, but real-time threat detection required efficient models that could process data quickly without compromising accuracy. They considered techniques like model pruning, quantization, and the use of lightweight architectures like MobileNet to reduce the computational burden. The team debated which of these techniques would offer the best balance between performance and resource efficiency for their specific use case. By the end of the day, Emily felt optimistic about their progress. The integration of CNNs into their cybersecurity system had already shown promising results in detecting malware, analyzing network traffic, and identifying phishing websites. However, the journey was far from over. Continuous advancements in deep learning and the development of more efficient CNN architectures were crucial for improving the scalability and applicability of these models in cybersecurity. In conclusion, the use of CNNs in cybersecurity demonstrates their transformative potential. The team's experience highlighted several key takeaways that could enhance their understanding and application of these models. First, the ability of CNNs to recognize complex patterns in data makes them particularly effective for tasks like malware detection and network traffic analysis. Second, successful deployment requires addressing challenges such as model interpretability and computational efficiency. Techniques like saliency maps and lightweight architectures can mitigate these issues, making CNN-based systems more transparent and resource efficient. Lastly, continuous learning from diverse and extensive datasets is essential for maintaining model effectiveness and adapting to evolving threats. As the team packed up for the day, Emily reflected on their discussions and the questions they had explored. She was confident that by addressing these challenges and leveraging the strengths of CNNs, they could significantly enhance their defense capabilities, protecting against an ever-evolving landscape of cyber threats.